Okay, hello and welcome to our lesson on combustion reactions. Combustion, when we think of that, we think of burning things. So these are reactions where we see the burning of a substance, but we can be a bit more specific in that. So a proper definition for a combustion reaction is the reaction of a substance with oxygen. Of a substance with oxygen. Pardon me. Okay, so these are always going to be your reactants. Is some substance with oxygen, and it always produces, well, it's burning stuff, so we know there's going to be heat, light, and the products are always going to be one or more oxides. Those being substances or molecules that contain oxygen. And we can break it down. In grade 11, we get a bit more specific than what we saw of combustion reactions in grade 10. And in grade 11, we'll see two types of combustion reactions. The first is complete combustion. So this is what happens when there is plenty of oxygen. So if there's lots of oxygen available for the reaction, then you will get complete combustion. And what that means is the substance is going to burn really cleanly, and it burns completely. So there's no smoke. If you see something burning without smoke, then there's complete combustion. There'll be no ash left over. No leftover ash. And the flame will burn blue. Okay, so this all occurs if there's lots of oxygen available. However, most of the fires we see and stuff burning is not complete combustion. It's in fact incomplete combustion. And this means other products have been formed. The reactant isn't used up efficiently or completely. So, and this happens when there's limited oxygen. And it's quite a bit more inefficient. So oxygen is limited. You get smoke and you get soot being produced. Think of black smoke being produced by a fire. That's incomplete combustion. You have leftover ash afterwards. Leftover ash. And the flame is yellow or orange. And that's all well and good, but what does that mean from a chemistry perspective? What are the products being produced? Because that's what we really care about. Well, there are general formulas for complete and incomplete combustion, and complete combustion is pretty straightforward, so I'll put that on the left. What you always see in complete combustion is some hydrocarbon. A hydrocarbon's a compound that has carbon and hydrogens in it, of varying amounts. There could be any number of carbons and any number of hydrogens, so I'm going to put in an X and a Y as variables there, because it could be C2H4, it could be C3H8, it could be C24H44. So we see things like that all the time. So it reacts with oxygen. And in complete combustion, you always only ever get two products. You will always get carbon dioxide and water. Always, all the time. It's pretty straightforward. These are always going to be your products of carbon dioxide and water. And then your job will just be to balance it. So that's pretty straightforward. And this here is a hydrocarbon, the name of that compound. Okay, so that's our general formula for complete combustion. In incomplete combustion, there are more than these two products. You do get other products. So this is going to be some compound plus oxygen. And here we get soot. Soot being produced. Soot is just solid carbon. So that's carbon by itself. Just elemental carbon is soot. And it's a solid. You get a poisonous gas called carbon monoxide. That's a gas. This is the reason that you have a carbon monoxide detector in your basement, because your furnace, when it gets old, can become inefficient, and when it's burning to fuels to heat your house, it can start producing carbon monoxide, which is undetectable to humans and very poisonous. So we put detectors in our basement to catch this. Okay, so these additional products can be created on top of the carbon dioxide gas. and water that we're used to in a combustion reaction. Other products can be produced as well. You'll actually probably never be asked to predict the products of an incomplete combustion reaction. In all of the questions you're going to get in grade 11, you can pretty much always assume it's going to be a complete combustion reaction. But it's good to know about incomplete combustion because it is a real-world problem. Okay, so as I said, if we're doing examples here, we're pretty much always going to assume that it is complete combustion occurring. So no matter what the hydrocarbon is, we always know that if it's reacting with oxygen, it's going to burn and it's going to produce the same two products of CO2 and H2O. So in my first example here, where I've got ethanol, that is alcohol, burning in the presence of oxygen gas, well, it's going to be complete combustion. So we know the products in our word equation are going to be the same two every time. So those are carbon dioxide and water. I can get those formulas in to get my skeleton equation, CO2 plus H2O. And now I just need to balance to get this. Oh, I should include my states as well. Carbon dioxide is a gas, and water is going to be a liquid. It'd also be fine if you put gas here, because realistically the water is going to be so hot when this is burning that it's probably going to evaporate. So liquid or gas is probably fine. And now we've just got to balance. So I'm looking at my left side. I've got 2 carbons. Always balance the carbons first is one of my hints for you here. You might remember from when we did balancing. I've got 1 carbon on this side. So I'm going to pop a 2 in front here to balance my carbons. I'm going to do my oxygens next. On my left, sorry, I'm going to do my hydrogens next, pardon me. Do hydrogens next and then do oxygens last. So my hydrogens, I've got 5 and 6 on this side. And I've got 2 on this side, so I'm going to put a 3 in front there to balance 6. And then my oxygens are last. So on my left side, I've got 2. And on my right side, I've got 4 plus 3 is 7. So I'm going to need, this is going to be a tricky one to balance here. 1, 2, 3, 4, 5, 6, 7. Yeah. So I've got 1, 2, 3 on this side. So if I put a 3 here, that's going to give me 3 times 2 is 6, plus my 1 in the ethanol is going to give me 7. And that's going to balance. Okay, so often the trickiest part with these is going to be your balancing, because the products are always going to be the same. Okay, let's do another one. We've got methane and oxygen gas. So our products are always going to be the same. Nice and straightforward. Carbon dioxide and water. Put my formulas in. CO2, remembering my states, it's a gas. And H2O, which is going to be a liquid. And now again, I just need to balance. So again, we'll do carbons first. I've got 1 on the left. And I've got 1 on the right, so my carbons are balanced. I don't need to touch those. Let's look at the hydrogens next. I've got 4 on the left in the methane. And I've got 2 in my water molecule over here. So I'm going to put a 2 in front there to make it 4, and therefore balance the hydrogens. And then my oxygens. So I've got on my left side, I've got 2. And on my right side, I've got 2 plus 2 is 4. So I can put a 2 there to balance that, and 4 oxygens. And that's balanced. Okay, and lastly, we'll do a tricky balancing one, and I'll remind you of a little trick of how to balance these. So I've got hexane burning in the presence of oxygen gas. So it's a combustion reaction. Doesn't say otherwise, so we can assume it's complete. Carbon dioxide and water as our products. And let's put in our formulas. CO2 plus H2O. The gas and the liquid. Okay, and this is going to be a tricky one to balance, but we'll give it a go. We'll do our best. So my carbons on the left, I've got 6. On the right, I've got 1, so I'm going to put a 6 there. Do our hydrogens next. I've got 14 on the left, and I've got 2 on the right. So I want to go with a 7 there to balance that out. And now I need to check my oxygens. So on my right side, I've got, let's see, 6 times 2 is 12, plus 7 times 1 is 7, plus 7 equals 19 oxygens. On my left side, I've only got 2 oxygens. So if I put a 10 in front, that's going to give me 20. If I put an 8 in a 9, that's going to give me 18. So I need to go in between. So what I want to do here in front of my oxygen is I almost want to put a 9.5. Because if I put 9.5 there, 9.5 times 2 equals 19. So that would balance it. And I can put that in as a placeholder, but I can't leave it. We can't leave a decimal. So what I'm going to do, just to use a little trick, is I'm actually going to multiply everything by 2. Multiply all my coefficients by 2 to get rid of my decimal. Times 2, times 2, and times 2. Okay? So, and this will get rid of my decimal and give me a nice balanced equation. So I've got a 1 really in front of my hexane, which I'm going to double to 2. My 9.5, I'm going to double to 19. I don't really have room here. Oh, didn't leave room, but I'll put a 19 there. My 6 times 2 is going to become a 12. And my 7 times 2 is going to become a 14. Okay, and we can double check that and it'll be balanced. I've got 12 carbons on the left, 12 carbons on the right. I've got 28 hydrogens on the left, 28 on the right. And I've got 38 oxygens on the left with 24 plus 14 is 38 on the right. So that's balanced. Okay, so that's often the trickiest part of many of these questions. Okay, and lastly, to wrap this up, one last reminder is that sometimes, well, the formation of metal oxides is also a combustion reaction. And we saw this in synthesis reactions. So to jog your memory, if we have something like, let's say, iron metal left in the presence of oxygen to rust, it's going to make iron oxide. Okay, so there's a synthesis reaction. However, by our definition, this is also a combustion reaction because we're seeing a substance in the presence of oxygen create an oxide, right? That was our reaction, a definition up here. It produces a reaction with oxygen that produces oxides. So this is also considered a combustion reaction as well. However, I think it's better classed as a synthesis reaction, but it's just good to be aware of and something to look out for.